The functioning of antennas is based on radiation. Radiation is an electromagnetic phenomenon. In fact, it is a wave, traveling wave. Like in any traveling wave, in radiation also there exists power flow. This power flow is measured, indicated by one of two quantities, power density, also called radiation density. Another quantity is radiation intensity. Power density or radiation density indicates power flow in terms of watts per square meter, whereas radiation intensity gives power flow as watts per steradian. The first one, power density, is a commonly used quantity for indicating power flow in electromagnetics, whereas the second one, radiation intensity, is used in some areas of electromagnetics, especially in antenna theory. Both indicate power flow. In that aspect, they are similar to each other, but there exist certain significant differences too between them. Power density is dependent upon the distance of field point from the radiator. Power density at a distance of 100 meters is different from power density at a distance of 500 meters. Radiation intensity, on the other hand, is distance independent. Intensity is same at 100 meters, at 500 meters, even at a distance of 1 kilometer from the radiator. Of course, both are density as well as intensity are direction dependent. Density, radiation density or power density, it is related to field intensity, radiation field intensity E, and this relation is E square by eta. E is field intensity, eta is intrinsic impedance of the medium. This relation has come from Poynting theorem or Poynting vector. Poynting vector gives power crossing unit cross-sectional area as E cross H. As radiation is a TEM uniform plane wave, E and H are normal to each other, and E to H ratio is eta. It makes E cross H equal to E square by eta. So power density becomes E square by eta. Power density is also related to radiation intensity through an empirical formula. Radiation intensity is radial distance square multiplied by power density. Hence, once we have field intensity E, we can find power density by using the relation E square by eta. From power density, we can easily obtain radiation intensity too using the relation radiation intensity is equal to product of R square and density, power density. Antennas, problems on antenna basics, part 3, series on antennas and wave propagation, lecture number 1.23. In the present session, right now, we consider several problems and their solutions. The problems being set on antenna basics. Primarily, the problems we are going to discuss about here are based on radiation intensity, directivity, beam area, beam width, etc. of antenna parameters. Now let us move to begin the course session. We start the session by considering a problem, example 1. The radiation intensity of a particular antenna is given by sine square theta. U is sine square theta. Theta is polar angle in spherical coordinate system. Calculate its directivity. We are asked to determine directivity from the radiation intensity. Solution. By definition, directivity is given by the formula D equal to maximum radiation intensity by average radiation intensity. This ratio can be expressed in terms of normalized radiation intensity as 4 pi over integral 0 to 2 pi. Integral 0 to pi un. Un stands for normalized radiation intensity sin theta d theta d phi. 0 to pi refers to theta, 0 to 2 pi refers to phi, azimuthal angle. For the given radiation intensity u equal to sine square theta, maximum value is 1. It is obvious, it doesn't require any further explanation. Hence, the normalized radiation intensity becomes equal to radiation intensity, given radiation intensity. Un, normalized radiation intensity, is U, which is equal to sine square theta. Therefore, Un is sine square theta. Substituting this expression for Un in the defining relation of directivity, which is given here, and performing integration, we can get directivity. So D equal to 4 pi over integral 0 to 2 pi, 0 to pi, sine square theta, sin theta, d phi. It becomes 4 pi over integral 0 to 2 pi, 0 to pi, sine cube theta, d phi. Performing integration and getting the value of the integral leads us to find directivity as 1.5. Another problem, example 2. The field pattern of an antenna is given by cos square theta. E of theta is cos square theta. Theta is in between 0 and 90 degrees. Find its half power beam width and beam area. Here field pattern is given. Field intensity is given. In the earlier problem, it is radiation intensity. Here it is field intensity. Solution. Part A, half power beam width. Here we try to estimate half power beam width. The field intensity E at half power points is 0.707 times its maximum value, which is 1. So at half power points, field intensity is simply 0.707. In the direction of half power points, cos square theta becomes 0.707. It leads to theta equal to 32.77 degrees. The maximum exists between half power points at theta equal to 0 degrees. Therefore, half power beam width is twice the separation between maximum and one of the half power points. It gives half power beam width as 2 into 32.77 degrees. It becomes 65.54 degrees. Let us try to visualize the problem. The given field pattern is like this. Something like at theta equal to 32.77 degrees. Somewhere here. At these 2 points, theta is 32.77 degrees. These are half power points. Half power beam width is twice the angular distance between radiation maximum and one of the half power points. In the present case, it turns out to be 65.54 degrees. Now, second part of the problem, beam area. From the basic definition, beam area is normalized power pattern integrated over a complete spherical surface. Therefore, beam area omega A is equal to 0 to 2 pi, 0 to pi cos power 4 theta, sin theta, d phi. Now, performing the integration leads us to get a value for omega A. In the present case, it is 1.26 steradians. Cos power 4 theta is power pattern, normalized power pattern. Sin theta, d phi is differential beam area. Now we consider another problem, example 3. Normalized radiation intensity of an antenna. It is given by sine theta sine theta sine cube phi, sine square theta sine square phi, sine theta sine square phi, sine square theta sine phi, sine square theta sine cube phi. Six cases are given, six different expressions are given for normalized radiation intensity. The intensity exists only in the region specified by theta in between 0 and pi, pi in between 0 and pi, and it is 0 elsewhere. Find exact directivity as a dimensionless quantity as well as in dBs. Before going to solve the problem, one aspect given in the problem has to be noticed. It says phi when it is in between 0 and pi, radiation intensity is non-zero. Otherwise, it is 0. So radiation intensity is 0 when phi is in between pi and 2 pi. Range of phi is 0 to 2 pi. Information given here says that intensity is 0 when phi is in between pi and 2 pi. Now solution. By definition, directivity is maximum radiation intensity to average radiation intensity ratio. It can be shown equal to 4 pi over integral 0 to 2 pi, 0 to pi un normalized radiation intensity sin theta d theta d phi. This is a differential solid angle or differential beam area. Notice in this expression 0 to 2 pi pertains to phi. This is general expression. But when it comes to the intensity given in the present problem, it is non-zero only when phi is in between 0 and pi. Therefore, limits of phi in this problem, they must be 0 to pi. 0 to 2 pi is general expression. Now, by using the given radiation pattern in the above relation, directivity can be obtained. While evaluating, the following mathematical relations are useful. Integral 0 to pi sine power n theta d theta. It is equal to 2k n minus 1 n minus 3 over n minus 2 into n minus 4, where k is pi by 2 when n is even, k is 1 if n is odd. Another relation, integral 0 to 2 pi cos power n theta d theta is equal to 2k n minus 1 into n minus 3 etc. Continuation is there over n into n minus 2 into n minus 4 etc. where k is equal to pi by 2 if n is even, it is 0 if n is odd. In both these relations, notice we have to keep on writing terms, several terms in the numerator as well as in the denominator. How many terms? It depends upon the value of n. Now we consider the actual solution process of the problem. We begin with the part A. Here, normalized radiation intensity is given as sin theta sin phi. Substituting this expression for intensity in the relation for directivity gives us d equal to 4 pi over 0 to 2 pi, 0 to pi. These limits are general limits, common limits. We come to specific limits just a little bit later. Sin theta sin phi is normalized radiation intensity, and one sin theta exists as part of a differential solid angle. So sin theta into sin theta, sin square theta and sin phi, d theta d phi. This is the expression for d. But it is said in the problem that intensity is non-zero only when phi is in between 0 and pi. So limits requires to be changed. They are changed here, 0 to pi. It should be square. Sin square theta, sin phi, d theta, d phi. Performing integration gives us a value of 3 pi by 2 for directivity. So when normalized radiation intensity is sin theta sin phi, Directivity becomes 3 pi by 2. Now we consider next part B. In this case, normalized radiation intensity is sine theta sine cube phi. Directivity becomes D equal to 4 pi over 0 to 2 pi, 0 to pi. 1 sine theta is in the expression of intensity. 1 sine theta is part of differential solid angle. Sine theta multiplied by sine theta becomes sine square theta, and sine cube phi, it appears as it is in this expression in the denominator. Now we have to consider appropriate limits for phi. As already mentioned, as far as phi is concerned, limits are 0 to pi. Reasons already explained. Now performing this integration leads us to a value of 3 by 2 for directivity. Similarly, we consider C part, where it is given normalized radiation intensity is sine square theta sine square phi. In this case, sine square theta is there. One sine theta is part of differential solid angle. So sine square theta sine theta becomes sine cube theta. Sine square phi, it appears as it is here. And limits on phi has to be changed from 0 to 2 pi to 0 to pi. So what we have for D is 4 pi over 0 to pi, 0 to pi, sine cube theta, sine square phi, d theta, d phi. Performing the integration gives us directivity as 3 by 2 for this case. Another part, fourth part D. Normalized radiation intensity is given as a sine theta sine square phi. Directivity, it becomes 4 pi over 0 to pi, 0 to pi, sine square theta sine square phi, d theta d phi. It gives D as 16 over pi. Another part E is considered. Here normalized radiation intensity is sine square theta sine phi. Directivity now is sine cube theta sine phi d theta d phi. Limits are 0 to pi, 0 to pi. It leads to a value of 3 pi by 2 for directivity. Now we consider part F. In this case, normalized radiation intensity is given as sine square theta sine cube phi. Sine square theta multiplied by sine theta appears as a sine cube theta. In the expression sine cube phi, it appears as a sine cube phi. Limits of F has been changed to 0 to pi. So 4 pi over 0 to pi sine cube theta sine cube phi d theta d phi. This is the expression for directivity. Evaluation of this expression gives us a value of 9 pi over 4 for directivity. Now we consider another problem, example 4. Normalized radiation intensity of an antenna is given. These intensities are same as the intensities which we encountered in the previous problem. Hence, no need to read out again. The intensity exists only in the region defined by theta in between 0 to pi, phi in between 0 to pi, and it is 0 elsewhere. Find azimuthal and elevation plane half power beamwidths in degrees. Previous problem is about directivity. We are asked to find the directivity from radiation intensity. Here we are asked to determine beam widths in degrees, in azimuthal plane, in elevation plane. Azimuthal plane means horizontal plane. Elevation plane means vertical plane. Solution. Azimuthal plane half power beamwidth. It is angular separation in phi. Phi is azimuthal angle between points where the intensity is half of the maximum. These 2 points are located at equal angular distance on the sides of maximum point. The half power band beamwidth, it should be beamwidth. The half power beamwidth then is twice that of angular separation between maximum point and one of the half power points. When it comes to elevation plane half power beamwidth, it is angular separation in theta. Azimuthal plane half power beamwidth is angular separation in phi, whereas elevation plane half power beamwidth is angular separation in theta, polar angle, between points where intensity is half of the maximum. These 2 points are located at equal angular distances on the sides of maximum point. The half power beam width then is twice that of angular separation between maximum point and one of the half power points. This information we are going to use in solving this problem. Now we consider the actual solution. We begin the solution process by considering a part where normalized radiation intensity is sin theta sin phi. First, we evaluate azimuthal plane half power beamwidth. In the present case, maximum is 1. Maximum of sin phi, here is sin phi, is 1 and it is along phi equal to 90 degrees. Phi 90 degrees refers to y-axis. This is x, this is y, this is z, this is 90. Phi 90. At half power points, sin phi has to be 0.5. It gives phi equal to 30 degrees. Thus, azimuthal plane half power beamwidth 2 into 60 equal to 120 degrees. Where is this? What is this 60? Notice, y direction is maximum radiation direction. Half power points direction corresponds to phi equal to 30 degrees. One half power point is along phi equal to 30 degrees, means it is somewhere here. This is 30 degrees. So angular distance between half power point and maximum radiation direction becomes 60. So half power beamwidth becomes 2 into 60, 120 degrees. One half power point is here, maximum radiation direction is here, another half power point naturally will be somewhere here. So twice the distance between, angular distance between half power point and maximum radiation direction. It gives the required half power beamwidth. Elevation plane half power beamwidth. In the present case, maximum is 1. Maximum of sin theta is 1 and it is along theta equal to 90 degrees. Theta 90 means this is theta equal to 90. Horizontal plane is one that corresponds to theta equal to 90 degrees. At half power points, sin theta has to be 0.5. It gives theta 30 degrees. Theta 30 degrees means it will be somewhere here. 30. This is 30. So maximum radiation is along a horizontal plane, in horizontal plane, and half power points are at theta is 30 degrees. Angular distance between half power point and maximum radiation direction naturally becomes 60. Therefore, half power beamwidth becomes 2 into 60 equal to 120 degrees. Another part, another bit of the problem. Here radiation intensity is given as sin theta sin cube phi. Azimuthal plane half power beamwidth. In the present case, maximum is 1. Maximum of sin cube phi is 1 and it is along phi equal to 90 degrees. At the half power points, sin cube phi has to be 0.5. It gives phi equal to 52.53 degrees. So the azimuthal plane half power beamwidth, it is 2 into 90. It is direction of maximum radiation minus 52.53. This is direction of half power point. It gives HPBW as 74.94 degrees. Elevation plane half power beamwidth. In the present case, maximum is 1. Maximum of sin theta is 1 and it is along theta equal to 90 degrees. At the half power points, sin theta is 0.5. It leads to theta being equal to 30 degrees. So elevation plane half power beamwidth becomes 2 into 60, 120 degrees. Continuation C part. In this case, pattern is sin square theta, sin square phi. Azimuthal plane half power beamwidth. In the present case, maximum is 1. Maximum of sin square phi is 1 and it is along phi equal to 90 degrees, along y direction. At half power points, sine square phi is 0.5. It leads phi equal to 45 degrees. So azimuthal plane half power beam width becomes equal to 2 into 45, 90 degrees. Elevation plane half power beam width. In the present case, maximum is 1. Maximum of sine theta is 1 and it is along theta is 90 degrees. At the half power points, sine square theta is 0.5. It leads theta being equal to 45 degrees. So elevation plane half power beam width becomes 2 into 45 equal to 90 degrees. Next part D. In this case, normalized radiation intensity is given as sine theta sine square phi. Azimuthal plane half power beam width. In the present case, maximum is 1, maximum of sine square phi is 1 and it is along phi equal to 90 degrees. At the half power points, sine square phi is 0.5, therefore phi becomes equal to 45 degrees. So the azimuthal plane half power beam width becomes 2 into 45, 90 degrees. Elevation plane half power beam width. In the present case, maximum is 1 as maximum of sine theta is 1 and it is along theta equal to 90 degrees. At the half power points, sine theta has to be 0.5 leading to theta equal to 30 degrees. So elevation plane half power beam width becomes 2 into 60 equal to 120 degrees. Continuation of the problem example 4. Part E. Here, normalized intensity is given as sine square theta sine phi. Azimuthal plane half power beam width. In the present case, maximum is 1 as maximum of sine phi is 1 and it is along phi equal to 90 degrees. At half power points, sine phi has to be 0.5 because half power points. It leads phi being equal to 30 degrees. So the azimuthal plane half power beam width becomes 2 into 60 equal to 120 degrees. Elevation plane half power beam width. In the present case, maximum is 1 as maximum of sine theta is 1 and it is along theta equal to 90 degrees. At half power points, sine square theta is equal to 0.5. It leads theta being equal to 45 degrees. So the elevation plane half power beam width becomes 2 into 45 equal to 90 degrees. Last part of this problem, F. Here normalized radiation intensity is given as sine square theta sine cube phi. Azimuthal plane a half power beam width. In the present case also maximum is 1 as a maximum of sine cube phi is 1 and it is along phi equal to 90 degrees. At the half power points, sine cube phi is 0.5. It leads to phi being equal to 52.53 degrees. So the azimuthal plane half power beam width becomes equal to 2 into 90 minus 52.53 equal to 74.94 degrees. Elevation plane half power beam width. In the present case, maximum is 1. Maximum of sine theta as maximum of sine theta is 1. It is along theta equal to 90 degrees. At the half power points, sine square theta requires to be 0.5. It leads theta being equal to 45 degrees. So the elevation plane half power beam width becomes 2 into 45 equal to 90 degrees. Now we move to another problem, example 5. A beam antenna has half power beam width of 30 degrees and 35 degrees in perpendicular planes intersecting at the maximum of the main beam. Find its approximate maximum effective aperture in lambda square, neglecting minor lobes. It is an interesting problem. Solution. The effective area of an antenna is related to its beam area through a relation. What is that relation? Product. Their product is always equal to lambda square. AE omega E. Product is lambda square. In terms of half power beam width of the main lobe, in the two principal planes, the beam area is given by this formula. Omega A is equal to theta HP, phi HP, steradians, where theta HP, phi HP are half power beam widths in theta and phi planes in radians. Thus, effective area is lambda square by beam area. Beam area is product of theta HP, pi HP. The effective area in terms of lambda square then becomes AE by lambda square, which is now 1 by omega A, which is equal to 1 over theta HP phi HP. It is given theta HP and phi HP. They are 30 degrees and 35 degrees, and they are required to be converted into radians. Then only they are suitable for use in this expression. So after converting them into radians, we have 57.618 whole square by 30 into 35. It gives effective area in terms of lambda square as 3.162. Note that it is a dimensionless quantity. Another problem, example 6. A ground station receiver has an antenna of effective aperture equal to 8,400 square meters. It requires a minimum received power of 3.7 into 10 power minus 18 watts for satisfactory communication. What should be the minimum transmitted power from a deep space probe situated at a distance of 800 million kilometers from the Earth? Assume isotropic transmitting antenna. This is a practical problem and an interesting one too. Solution. If the power transmitted by the probe is Pt watts, power density S on Earth becomes Pt over 4 pi r square. R is the distance between probe and Earth. Pt is transmitted power. Distance is given as 800 million kilometers. 800 million kilometers. So S is Pt over 4 pi into 800 into 10 power 6 into 10 power 3 whole square, with an effective area equal to 8,400 square meters. The receiving antenna gives out a power PR equal to power density into effective area. Power density is, we have already calculated. Effective area is 8,400 square meters. So received power by the antenna is this. This must be at least equal to 3.7 into 10 power minus 8. So equating this expression, receiving antenna's power to 3.7 into 10 power minus 8, we obtain an equation. In this equation, only unknown is Pt. Solving this equation for Pt, we get a value 35.44 into 10 square watts for Pt. So minimum transmitted power by deep space probe must be this much, 35.44 into 10 square watts. Another problem, example 7. An isotropic antenna to produce 1 milliwatt per meter square at a distance of 2 km in a given direction requires to radiate 2.4 kilowatt, whereas a directional antenna requires only 180 watt. Then find the directive gain of the directional antenna. Solution. Given that power transmitted by the isotropic antenna is 2.4 kilowatts, power transmitted by directional antenna is 180 watts. Therefore, directive gain of the antenna is ratio 2.4 kilowatts to 180 watts, 2400 watts to 180 watts. It comes out as 13.33. It is a dimensionless quantity. It can be expressed in decibels by applying 10 log over 13.33 to give 11.25 in dBs. With this, we come to the end of the present session. In this session, the focus has been on radiation intensity, directivity, beam width, beam area, etc. of antenna parameters. Hope this session is useful to you. We meet again in another session soon with a new topic.